Alright, in the previous lecture, we learned how to derive the equation for vertical stress in a semi-infinite medium. And with this equation, now we can calculate vertical stress. The question is, what are the horizontal stresses? And that's what we're going to see now. Before we jump into that, let's just remind ourselves about what the principal stresses are. Any tensor with diagonal and off-diagonal terms, like the one I'm writing right now, is going to have a set of principal stresses. Those principal stresses can be found mathematically by calculating the eigenvalues of the matrix. And if we say this is a symmetric matrix and it's populated with all real numbers, then we're going to be able to find the principal values or the eigenvalues, and we denote those with sigma 1, sigma 2, and sigma 3. Notice that we just use one index to denote the principal stresses opposite to the general stress tensor in which we use two indices. Associated with these principal stress values, remember that we also have directions. For example, the tensor on top is written for a particular coordinate system 1, 2, 3. And in order to find the principal directions, we also usually calculate for those two what are the principal directions. That means that this new tensor, which is basically the same but just written in another coordinate system, has associated with it a principal direction base. And this principal direction base, let's say I'm always following the right hand rule, let's say is 1, and we're going to call it 1 star, 2 star, and 3 star. And here you can try to do this with me. Remember, in order to follow the right hand rule, your index finger is number 1, your middle finger is number 2, and your thumb should be number 3. And notice that this is aligned and respects the coordinate system that I have just drawn. And this just works with your right hand. You'll see that it doesn't work with your left hand. So this is the convention that we are using. All right. When I write the stress tensor as principal stresses, usually the maximum principal stress sigma 1 goes on the top left, and this maximum principal stress is going to be equal or larger than the intermediate stress sigma 2, and this is going to be equal or larger than the least principal stress sigma 3. As you can see also in the coordinate system, these elements of this base are all perpendicular to each other. That's a condition that we use for this Cartesian coordinate system. And in this Cartesian coordinate system, the principal stresses are going to be always perpendicular to each other. Okay, so now let's go to a case, a particular case out of a principal stress tensor. And in this case, what I'm going to assume is that sigma v is a principal stress. This condition is valid when we have a free surface, which is horizontal, and we are in an isotropic medium, similar to what we had in this particular example. Because this is a free surface, we cannot have any shear stresses, and since this is isotropic and there are no changes in lateral directions, the vertical stress has to be a principal direction. And in that case, if the vertical stress is a principal stress, then horizontal stresses are going to be principal stresses too. Let me tell you, this is not always the case in the subsurface. Most times, vertical stress is very close to be a principal stress, or to the principal direction is very close to be in vertical direction. But sometimes this is not the case, and we're going to see that later on. And it's very important to know that in some cases, your vertical stress may not be a principal stress. But for the moment, let's assume that vertical stress is a principal stress, and therefore, if vertical stress is a principal stress, then sigma v is going to be perpendicular to two horizontal stresses, which are also going to be principal stresses too. Two horizontal stresses, which are going to be principal stresses. And from these horizontal stresses, the maximum principal stress, I'm going to denote it with capital H. I'm going to call it sigma H max. And this is going to be perpendicular to another horizontal stress, perpendicular to sigma H max, perpendicular to sigma V, that is going to be sigma H min. All right, so let's see how then we will write such a stress tensor. In this case, now that we have sigma v as a principal stress, then we say the horizontal stresses are going to be principal stresses. And let me move over here to this screen. We're going to start talking about three different cases, and we're going to see the explanation for that. One is going to be called normal faulting, and in this case, the maximum principal stress is sigma v, which is going to be equal or larger than sigma h max, which is going to be equal or larger than sigma h min. In such case, the stress tensor, if I write it as principal stresses, is going to be like this. This is a tensor of principal stresses. And because these are principal stresses, all the off-diagonal terms are equal to 0. We're going to have two other cases. The second one is called strike slip. We'll see the reason of why the names are called like that in a minute. And in this case, the intermediate stress is the vertical stress, and the maximum and the minimum are horizontal stresses. Now you may start wondering, how is it possible that horizontal stresses are higher than vertical stress? Okay, it is totally possible, and we'll see that in a minute. What is the reason for that? And the other possible case is called reverse faulting. And in this case, now the least principal stress is vertical. And the stress tensor will be written like this. All right. These are the three possible cases that we can find in the subsurface. There are some places in which, even in the same sequence, you can find variations of the stress regime going, let's say, from strike slip to reverse. And it's actually the case that I have presented in weekly project number 1. All right, before we move on, I'm going to do one more clarification, and is the convention that we use to talk about effective stresses that usually they go with sigma and total stresses that we're going to denote it with S, where the total stress is a result of the effective stress tensor and pore pressure added only to the diagonal elements where this I is the identity matrix. So in those conditions then, the matrix that I just wrote can be written as SV, SH max, SH mean. I'm going to skip writing the zeros for now. SH max, SV, and SH mean. And finally, SH max, SH mean, and SV. Where, for example, SV is equal to sigma B plus the pore pressure. SH max is equal to sigma H max plus the pore pressure. And finally, SH mean is equal to sigma H mean plus the pore pressure. We're going to see in detail later on the distinction between effective stress and total stress. But I like that for now we just accept this convention and these equations, and remember that the vertical stress that we calculate with the equation that we had before, which is called the lithostatic gradient and takes into account the bulk density of the rock, serves to calculate the total vertical stress, accounting for the weight of the water within the pores and the rock itself. This is a total stress, and we denote it with S, and effective stress are going to be denoted with sigma. All right, so let's see why this classification now is important. Let me complete the zeros over here, and we'll see that. All right, so let me continue these lines over here. Remember, normal faulting, we have it on the left, strike slip in the middle, and reverse on the right. In a normal faulting type of in a normal faulting site, what you would expect is what is called a normal fault. If SV is a maximum vertical stress, then you would have something like this. Here I'm drawing a block diagram of a formation. Let's say that we have a wellbore that goes into this formation, and here we have a fault. In normal faulting, as we were saying, the maximum principal stress is going to be vertical, and the minimum horizontal stress are going to be horizontal, the intermediate and the minimum. So SV is the largest. Let's assume in this particular case that SH mean, the minimum horizontal stress, is, let me use another color, is in horizontal direction, and it is in this particular direction. And SH max is in this direction. Let me make sure that my SV is larger than the other two. In a site with normal faulting, then you would expect a normal fault where the hanging wall slides down relative to the foot wall. The foot wall is what is below the fault. The hanging wall is what is on top. And also, if you were to have a hydraulic fracture in this case, the hydraulic fracture is going to be always perpendicular to the minimum principal stress, which in this case is SH min. So in that case, if we were to have a hydraulic fracture, this one will open perpendicular to the direction of SH min, and growing out of the plane would look something like this. Remember, this is growing out of the plane, and it's going to be perpendicular to SH min. Let me add a few more details to my block diagram so it looks a little bit more realistic. This is a 3D block diagram. And this is our fault over here, which is sliding down relative to the footwall. And let me add one more thing over here. This is the formation that we're interested in. This is a case of normal faulting. In a case of a strike slip, now vertical stress is going to be an intermediate stress, but still the minimum horizontal stress is going to, the least principal stress is going to be horizontal. So in that condition, what we would expect would look something like this. This is another block diagram. I think this is going to be a little bit more challenging. So let me use a little bit of help here. All right, so our formation is going to be somewhere over here. Let me delete this. And I'm going to make this one slide like this. The difficult part here is to draw the fault. Okay, so I think we're good. All right, so let's draw a wellbore again that goes into this particular formation. We draw our drilling rig in a strike slip. Then now the maximum horizontal stress is going to be the maximum principal stress. So this is going to be SV, intermediate stress, and let me use a color code for this. The black is going to be the maximum. So now the maximum is going to be SH max. Intermediate is going to be SV. And the minimum is going to be SH min, which arbitrarily I chose it to be in this direction. All right, in that case, let's start explaining the hydraulic fracture. Hydraulic fracture is going to be always perpendicular to the minimum principal stress, which in this case is SH min, same as in the other case. So we will still have, in this case, an ideal hydraulic fracture that will grow perpendicular to the minimum principal stress, in this case SH min. If we were to have a fault in this case, it's going to be different. Now the fault is going to depend on a combination of SH max and SH min, because in this case SH max is S1, and in this case the fault is going to produce a movement of these blocks along the strike of the fault. That's called strike slip. The strike of a fault is this line over here, which is the intersection of the plane of the fault with the horizontal plane. That's what is called the strike. And because this fault is moving along the strike, that's why it's called strike slip. In these two cases, remember that a hydraulic fracture, if it were to grow, is going to grow vertically and perpendicular to the minimum horizontal stress. The faults in this case will be different, but the hydraulic fracture will be the same. And last, in the reverse fault case, then we will have in a scenario which is completely opposite to the first one and also to the second. And it's going to look something like this. Let's say that we have a formation over here, and we're going to add a little bit more of reality to this plot. And okay, this one will be real. Let's draw our wellbore. Probably here we don't want a horizontal wellbore, so I'm just going to draw a vertical wellbore. And I think this is more or less good for now. All right, if we were to do a hydraulic fracture in this place, now the least principal stress is going to be vertical. The maximum horizontal stress is going to be horizontal. And let's say this one is SH max. It's equal to S1. The minimum horizontal stress, we'll do it with red, SV, and the minimum horizontal stress is going to be the intermediate stress, SH min. If we make a hydraulic fracture in this case, then this is going to grow perpendicular to the least principal stress. Therefore, in a site subjected to reverse faulting, a hydraulic fracture would tend to grow more like a pancake in horizontal direction as a horizontal plane perpendicular to the vertical direction, and going out of the plane is going to look something like this. And if we have a fault, this fault is going to tend to move such that the hanging wall moves upwards relative to the full wall. You may wonder why this is the case, and it's a little bit easier to see it in this particular plot. This is because of SH max. Notice that SH max is the highest. So when it pushes and compresses the subsurface, it's going to make these fractures which are somehow contracting the subsurface. So these blocks, this one, the hanging wall is going to move on top of the footwall. And this is going to result in something like this. So here I'm going to assume there is some erosion, so this rock is not hanging over there, and it's going to look something like this, where now our formation is over here. I hope that you see right away why it is very important to get to know what is the fault regime in which we are, or in which a particular project is going to be done, because that's going to change significantly. First, what is the potential direction of a hydraulic fracture? And second, what are the faults or fractures that are most likely to be reactivated or are going to induce micro seismicity or seismicity in those particular cases? And that's intimately linked with the type of stress regime. From now on, just to make it shorter, remember this is normal faulting, and we're just going to go with this by NF, strike slip, SS, and last reverse faulting, RF. All right, so this is it for this video.